Just let it get started, the gamma function, hopefully. We can go slightly faster. I mean, we can skip some of these things. Again, it's impossible to divide everything. You just try to get familiar with this object, mathematical objects. Just like when you first learn sine and cosine, you may be not familiar, and then you get confused and that all that. But once you get used that so many times, you sine and cosine, all these elementary function becomes easy. And just like these so-called special function, at first it may feel strange and not familiar. Then after you use it for a while, you just you could use it just like sine and cosine or all that. There's nothing very special about that. So the gamma function, there are several different definitions. Your textbooks start with this infinite limit. That's the Euler formula. But we may actually start with integral, because that's the most likely part that we define a function. Because sometimes if we found integral or we found a certain form of integral that appear quite often, then we don't want to keep writing this as an integral. We just give it a name, right? So in this case, there's a function e to the minus t in the integram, and t z minus 1 dt integrate 0 to infinity. So that integral, obviously the t goes to infinity because of the exponential function. That should be well behaved. So the limit exists, right? And then when the lower limit t goes to 0, and so you don't want it to be less than -1, right? So there's a limit that so this cannot be less than -1. So that there's a restriction for this integral to exist, will z greater than 0, because this is must be greater than -1, right? And but that is the restriction imposed on the integral form. Doesn't mean that gamma function doesn't define with a real z less than 0. It's defined for all the complex plane except for the singularity. You see that they have a gamma function has some simple poles, actually infinitely many simple poles at the negative integer. All the negative integers are not defined, right? And we actually include 0 and negative integer. And we see that. So this is like first you define a function using integral with some restriction, but then later on we just generalize it to a more general form that remove the restriction. Okay, it's like what we did in the complex variable chapter. We call it analytic continuation. Basically, we continue to complex plane. Say this integral might be at first defined with a real z, but then you can extend it to a compact z, right? And then later on, you even remove this restriction, but not using the integral formula, right? And so that's one definition. And following by two more integral form, which is basically just change a variable. Say like the next one is just basically called t becomes t squared, right? If this becomes t squared, this e to minus t squared, this becomes t dt, right? And then that combined with this one, right? And again, this becomes t squared to t 2z minus 2, and then you have t, so t2 t minus 1, right? And then so you can. The next one is just a very simple change of variable, but although it's trivial, the change of variable is useful because of this e to the minus t square that give you something like a Gaussian integral, especially once for special value of t of z, like for z is 1/2. If z is 1/2, then you cancel with the 2, the 1 minus 1 is 0, so you don't have the t factor. This becomes a half of the Gaussian integral, and you know the value, right? And so that is important to give you a special value. And another functional integral form is this one. It involves another change of variable, which is very straightforward. I think this is a homework problem, so I'll just write it down and you work on the homework. Okay. So just do a change of variable, you know that. Of course, this is just a 2 example. You can keep doing change of variable and then find out many different integral form that is still just the gamma function. Okay. All right, and like I said, this function will give you a gamma 1/2 is square root of pi, because that's just a result of a Gaussian integral, right? And that actually is important. All right, then this form is changed to the first definition in your textbook 13.1 by this a little argument, this by a certain limiting process, right? So we'll go back to here after. So go back to this integral form. And we'll try to get to that definition, which is has a nice form, and then we use that to divide another definition, which is an infinite product, and then that infinite product will allow us to find the derivative of the gamma function easier. Okay, so there's some reason for going through this process. So and then to just going through this process, so that because the two definitions look so different, so you may wonder why they are the same. But you go through this process, then you show that they have reason why they are so different, but they are still the same. Okay, so the argument is like because you have an e to the minus t, then you use the usual limiting process to define the exponential function. This is n goes to infinity. Get this first. E to the minus t is 1 minus t over n, the power n. So this one, take a limit of n goes to infinity. This n in here will be just e to the minus t. Right, and then you have this the rest of this minus 1d 18, right? And then because we are already taking n goes to infinity, we might as well change this upper limit to n, because you integrate 0 to infinity anyway. But if n goes to infinity, so we cover that. We cover this upper limit going to infinity. Okay, so that is what that is. This form. This is defined in your textbook as this function f as a function of z but n. I should actually say c to the n. This is defined as f c to n. And then you take the limit of n goes to infinity. Okay. And then so we define fc, this object as this one. Okay, this is this f. And we can evaluate this one by the integration by parts, right? And then but easier to do a change of variable first. So define this is your f. So f using define u as t over n, right? So f n. So t over n is your u, so 1 minus u power n. And now that the t is n times u, so t is 0, u is still 0. And when t is n, u is 1. Just change 0 to n to 0 to 1. Okay. And then t is n times u, and then t minus 1 power. The dt will be n du dt then. Okay, and we can now take out some of the constant out. So there's an n here, right? There's n to the z, and n cancel with this minus 1, so it's only n to the z, right? And the rest is u to the z, right? And then you can write f z and take the constant out, right? By n z 0 to 1 minus u n u to the z du. Okay, so we do integration by parts. So the first is writing this u c minus 1 because cancel this n but not cancel this one, c minus 1. Right? This u to the c minus 1, so u to the z minus 1 is d du u z 1 over z, right? This one is just this one. And we use that to do the integration by parts. And so it's 1 minus u to the n over z uz, right? And then that's the 0 to 1 minus this z, also this, you keep the z and then take the derivative of that. That is n, and integrate 1 minus u to the n minus 1, and then that becomes uc minus 1. Okay. Minus. Say that again. Where's
So minus u, so what did that become as plus?
Where's minus u?
1 minus u, so
Oh, 1 minus u, yeah, 1 minus u, you take the derivative and then there's another derivative, okay, become plus. Yeah, wait. Yeah. And then But you evaluate this, the boundary term, when u is 1, so this you have this 1 minus u term, so that q, this the upper limit. Lower limit u is 0, so you have u to the power z, and as long as z is positive, then that is also 0. So you get rid of the boundary term. Okay. So basically, this one gives you n over z multiplied by another integral of the same form. This same form has the property that the 1 minus u term decrease by 1, the power decreased by 1. And this is c minus 2. U z, no, that's c minus. This increased by 1. It's increased by 1, and that's decreased by 1. This increased by 1. Right? And so you can keep going the same process. So you n the z. The next one will be this n becomes n minus 1 because this is compared to this one. So n minus 1. Then whatever z here becomes z plus 1 because compare this with that, right? So whatever the old z becomes a new z plus 1, right? And then you can keep going. So n plus 2, n minus 2, z plus 2, all the way up to a final term. I think finally, you reduce all of them, there will be n of them. So the first one reduced by 1, you reduce it all the way, and do it n times, will make this to be 0, right? And then multiply by 0 to 1. So that would be 0. And so the first time it becomes 1, right? So basically, do it n time becomes u to the n, z plus n. And there's a minus, Why is it c minus 1, z, this is a 1, plus 0, that's the first term is it becomes z, so they get z plus 0, and the next term becomes z plus 1, so n plus 1, n minus 1. Oh, yeah. And then now this one is just a power, so you evaluate that. What is that? U to the c minus c plus n divided by c plus n, right? You just take the integral of this one, right? C plus this c plus n, right? And then evaluate as 0 to 1. 0 is still 0. The lower limit is still 0, right? The upper limit is 1. The c plus n is still 1, right? It's still 1.
Where did this product of n come from?
What product of n?
Or from the second to last line to the last line. I'm sure.
This one? Second to the last line, this one?
Yeah, that one's the one below it. I don't. Where does the n over?
So this is integration by parts, right? So this one, basically you use this, what I did here. This u to the z minus 1 is this one, 1 over z du z du going to here. So this one, this going to here. I probably should write another line, just save some writing over here. And then this becomes integration by part. The integration by part becomes this one divided by z multiplied by this one. This 1 minus u to the n divided by z multiplied by this one. And evaluate the two limits, 0 to 1. Right? And the minus the derivative of this one multiply, I should say, derivative of this and then the z term. but the z doesn't involve in u. That doesn't matter. Z is just a constant for this purpose, and then multiplied by u to the z. The u to the z multiplied by the derivative of 1 minus u to the n divided by z. The 1 minus the derivative of u, because the 1 minus u to the n power, right? So you got n multiplied 1 minus u to the n minus 1 power, but then take a derivative of the argument, you get the minus sign, cancel the minus sign, become plus. So you become n divided by z. And the rest is of this form. The trick is identify this as the same form as the original integral, except that the power of the 1 minus u term decreased by 1. The power of the u term increased by 1. Okay, and then you can keep this process going until you get rid of this n. Yeah, you do it n times, then n minus n becomes 0. That's the factor, whole factor is just 1, right? And that becomes this one. But finally, evaluate this integral, which is this simple power integral. And that gives you this one, and then upper and lower limit give you just 1. Okay. So you basically just now you can get rid of that and say that because you are doing the n, let me just not erasing, just keep writing it as n minus 1, n minus 2, all the way to say it again.
n minus 2.
n minus 2
n minus 1. Did n minus n minus.
to 1. I mean, right? Because you keep decreasing it, right? And you do it n time, right? You don't want to get to 0 because one time becomes n minus n, and you get n minus 1. Before you do it, before you get to this, that would be n minus n. Before you do that is, after the final one is 0, but before you do that, it is 1, right? Right. That's the n time, because n, this is the first integration by part, give you this one. The second one give you this one. So the n one will give you this one. Okay. And now the c is c plus 1, c plus 2, all the way to now figure out what is should be because they're all plus and minus, right? Each time is plus and minus. One is n minus n, n minus n minus 1. So it should be z minus z plus n minus 1. And I take that back. This is 1. Because you have a z, you still have a z. The final one, you have c plus n. Yeah. Okay. So did that give you the exact form of this f? But then gamma function is taking this limit n goes to infinity. So now you can just write it out explicitly, and that should be the form. I mean, multiply by this factor. Give you in the textbook, just inverse this product 1 to n, 1 to z to n, and then you have z plus 1 all the way to z plus n, and then multiply by this factor, and this is z power. Well, I'm out of time. Okay, this is the Euler formula. And take the limit of n goes to infinity. Okay. At least that's we tie up the integral formula with this limit of what they call infinite limit, right? And then this limit, of course, you need to show that this limit converge, but assuming that is convergent, there's some indication that that should converge, because as n goes to infinity, every time you just multiply by something that's very close to 1. So so that should give, and I mean, it's not a proof, but then it's likely it's converging, right? And that give you the integral form. Right, okay, we'll stop here because I'm totally out of time.